Thank you for joining us once again. I'm really looking forward to this morning's lecture. When I was putting together the program a little while ago, I was trying to find, as we usually do, a really good diverse section of researchers and scientists and engineers to talk to us about a whole wide range of stuff. And I thought, do you know what would be really, really good? There's been a lot of stuff happening over the first half of this year around Mars. Like everyone seems to be going to Mars at the moment. We've got NASA's got a new mission which has touched down as roving around on Mars. They've got a little helicopter and everything. It's amazing. We've got China up on Mars now. We've got the Saudi space team have got an orbiter around Mars at the moment. It seems like everyone is going to Mars. Mars is where it's at. And so I thought we should have someone to talk about Mars. Let's do that. And so I got in contact with a few people that I have contact details for over in America at NASA. And they put me in touch with today's speaker who said, yeah, I'll come and have a talk to you. Oh, okay. So it's really nice to meet you, Emily. What do you do? And Emily, this is Emily Judd. She's an aerospace engineer at NASA Langley Research Center. And she's got one of the best job descriptions I've ever come across in my life. So imagine this for a second, right? You go to a party and someone says, what do you do? And you say, well, I'm the deputy team lead for Langley Research Center's Mars architecture team. Oh, really? What's that? Well, I work on the challenges of sending astronauts through deep space to another planet. Oh, cool. You're like, how good would that be? So would you please make very, very welcome in the time-honored tradition of banging your hands together in whatever space you're in. Please make very, very welcome Emily Judd, aerospace engineer at NASA. Emily, welcome to the ISS. It's really nice to have you here. Thank you for joining us. Please do tell us about your work. I'd love to hear about it.
Well, sure. Thanks for inviting me. I'm really excited to talk with you all about what NASA's been up to for planning out some human Mars exploration. So, as we said, I'm going to be talking today to you all about human Mars exploration. So some of the missions that got mentioned previously were about the robotic missions that have been going to Mars and roving around the planet, orbiting around the planet. But all of those are kind of in prep for, the ultimate goal of sending humans there. So that's what I'm going to be talking about today. So before we get into, some of the technical details, just a little bit about me and how NASA is set up. I'm here at the NASA Langley Research Center, which is one of quite a few different NASA centers spread all across the US. And within NASA, we have what are called different mission directorates or different areas that NASA likes to focus on. And so the area that I'm working in is called the Human Exploration and Operations Mission Directorate. So that's all of the human exploration with the astronauts, going to the International Space Station, looking at returning to the moon with the Artemis program, all of those types of things. And as part of that, I'm on the Mars architecture team. So looking at specifically, how can we go on to Mars? So how did I end up in engineering? So I would say, my path here has not been kind of the normal path to engineering. When I was in high school, although I was really good at math and science and I enjoyed those topics a lot, I was much more interested in kind of the humanities, being involved in band and choir, was also an athlete, played on the volleyball team. So when I was signing up to go to college, I applied as a music major. And so when I got to school, I was at the University of Central Florida, which is very close to another NASA center, the Kennedy Space Center. And that's where NASA launches most of our big missions. So just by being in that location, I was exposed to what NASA does. And I thought, oh, rockets, this stuff is really cool. Maybe I should figure out more of what's going on here. So while I was there, I kept kept involved with music, ended up getting a degree in that, but also picked up aerospace engineering. So you can see the picture on the left there is me with our school mascot, and he's holding a rocket from our rocketry club. So that's kind of how I got into aerospace, kind of, a roundabout way, but had a lot of fun there too. So after undergrad, I realized I still needed to learn a bit more about what aerospace was really all about and figure out what area I wanted to focus on. So I applied to go to graduate school so I could get some more of those specialized skills. And so for that part, I was at the University of Michigan and again did 2 degrees because I have problems picking what exactly I want to do when I grow up. And so I got a master's in climate and space sciences and engineering, focusing on planetary atmospheres, particularly looking at the differences between Venus, Earth, Mars, and Jupiter. And then after that, I realized, okay, maybe the hardcore space science is maybe not the best fit for me. And I maybe like doing more of the engineering side of things a bit better. So I stayed around for another year and picked up a second master's in space engineering. And that topic area really spoke to me and was a really great fit for my skills and my interests. And that's how I ended up here at NASA Langley in our space mission analysis branch, where we do all sorts of space analysis, space engineering. So it fits exactly with what that program was teaching me. So since I know you all are from Australia and might not know where all these places are, here's a little map to help you orient yourself. So down here at the bottom is the Gulf of Mexico, and then we have the Atlantic Ocean off to the right here. So Iowa is kind of smack dab in the middle of the US, highly agricultural area, pretty rural area. So then I went down to Florida for undergrad, popped back up north for grad school, and now I'm out here right on the East Coast now at the NASA Langley Research Center. Mars is approximately 1/3 the size of the Earth, so your gravitational force on the surface is much less. So, walking will feel a lot different for the astronauts. Just general operations on the surface will feel a lot different. As an astronaut yourself, you will weigh a lot less on Mars. And kind of the rough approximation is it's about 1/3 the difference from here on Earth. Volume-wise, takes up about 6 of Mars to make 1 Earth. Mars has 2 moons, Phobos and Deimos, both very, very small moons. And there actually have been some interesting mission concepts proposed of what would happen about sending astronauts to one of the moons here. But you can imagine with the moons being so small, the gravitational effects would have a much, much larger impact on those surface missions. So a few other differences you can see here between the planets. The atmospheric composition is a lot different, whereas Earth is primarily nitrogen and oxygen, which is what allows us to breathe. Mars is primarily carbon dioxide with a little bit of some other stuff mixed in. So, astronauts would always have to be in their spacesuits when they're wandering around Mars, just, to help them stay safe, be able to breathe, so they're not inhaling any of the dust, any of that stuff too. You can also see the temperature ranges down here on the bottom. And a fun thing that you can see, there is some overlap. Even though Mars is so much farther out in the solar system than Earth is, at times, places on the Earth, depending on how the weather is, can actually be colder than places on Mars, which is a really fun fact when you get that popping up in your weather saying, hey, today in Canada, it is colder than Mars. So, what is NASA planning for sending astronauts, sending humans to Mars? The current mission concept is that we're going to send 4 crew members, and that's a mix of male and female astronauts. This could include some of them staying in orbit around the planet and some going down to the surface, or a mix of both. Just depends on how things shake out. So how are we going to be accomplishing that? So there's going to be, several pieces that will have to all come together to make this mission work. So we'll have the transit portion, how do we get from Earth vicinity to Mars? So that'll take a big transit vehicle. Then we'll also have how do we get down to the surface? How do we stay safe while we're exploring on the surface? And then how do we get back after that? How do we get back up off the surface and return home safely? So the where. So this takes place in lots of different areas that haven't had astronaut exploration before. So, we're going to, be around Earth, in the Earth vicinity. We're going out into deep space on our way to Mars, and then we'll have the exploration around Mars in orbit and on the surface. This could happen as early as sometime in the 2030s. The current kind of mission plan is that the round trip would take about 2 years. And this would include 30 sols on the surface of Mars. And so a sol is a Mars day. So just terminology there. And one nice thing about Mars is that a sol is actually only about 37 minutes longer than an Earth day. So it's not, a big change for the astronauts to get used to. And kind of essentially for mission, timeline planning, generally that 37 minutes gets baked in as free time for the crew, or extra time if stuff takes longer than expected. Now, why do we want to go to Mars in the first place? Well, I kind of believe that one of our intrinsic characteristics as humans is that we always want to push further. We want to keep exploring. We want to keep finding out more and more about where we are in the universe. So, by developing the technologies that are needed to go to Mars, we're helping improve life here on Earth. We're finding more about what makes the solar system, how it's different than, other solar systems wandering around. Just a lot of really exciting things to look at. Now, how are we going to do this? So, kind of contrasting with the robotic missions like the rovers or the orbiters that are currently at Mars, those missions, they don't have to worry about trying to come back. They also don't have to worry about trying to keep these pesky humans alive. Humans are very needy. We have to breathe, we have to eat, we have to drink, we have to sleep. So many things that we have to include to take care of the humans. So in order to keep the humans alive and happy, we are going to have to send things in advance, because to send everything all at once would be this gigantic system that would be really, really difficult to build. So there's going to be cargo missions that will be sent out ahead of time to make sure that all of the food, well, maybe not all of the food, but some of the systems that will be going in advance will be there, ready and waiting for when the crew finally gets there. And then, then we'll have all the vehicles that the crew will use, such as, a pressurized rover, where they will spend their time on the surface, their ascent vehicle to return back to Mars orbit, their different spacesuits, all of those types of things. So we talked a little bit at the beginning about, your transit vehicle. How are you going to get from Earth vicinity to Mars? So this is our current concept for our big transit vehicle. And so, since it's so large, we're going to have to use a combination of different types of launch vehicles. So that could be, commercial launch vehicles, what NASA's new rocket that's currently in development, the Space Launch System, which is going to be a huge heavy lift rocket in order to, be able to lift these large payloads up to space. Just for a concept of distance, the round trip from here to Mars is about 2,000 times farther than a trip to the moon. So just for scale, just think about how many kilometers that would be. I think the number came out to be 1.8 billion kilometers for a round trip to Mars. So it's a pretty hefty trip there. Another big challenge is that the landed mass that we have to do, the Curiosity rover, which is very similar to the newest rover, the Perseverance rover that just landed back in February. The mass needed to keep the humans alive and for this exploration plan is over 20 times the mass needed to land one of the big rovers. So that whole 7 minutes of terror with the communications delay from getting back to Mars to the Earth, that's going to be a much bigger deal, because if your Mars ascent vehicle crashes, you're going to have a very, very bad day. So just challenges are getting bigger and bigger, just requiring so much more to take care of the humans. I'm guessing this video is not going to work just due to the bandwidth issues. So we'll see if I can just play a little and then pause it. Okay, so we'll just pause it there so there aren't hopefully audio issues. So this is kind of just to give you a little scale. So we, the solar system here, the distance from the sun to the Earth is what we call 1 astronautical unit, 1 AU. So about, 150 million kilometers on average. Earth's orbit is pretty circular, so that's a good approximation. For Mars, Mars orbit is a little more oval, a little more elliptical, but again, on average, it's about 1.6 AU. So you can see just looking at the distances, it's a lot farther out there. Oops. Okay, so about here, so you can see that with how orbital mechanics work, you can't just fly in a straight line to the planets, because as you head out, Mars is also moving. So you kind of have to take this nice path and catch up to Mars on your way out there. Okay, so let's see if there we go. So once you get to Mars, then you can see also, you're not going to be able to just go straight back to Earth when you want to leave, because now Earth and Mars are again moving. So depending on what propulsion system you pick, whether that's a chemical system, whether that's a nuclear system, whether it's a combination, whether you're using electric propulsion, all of those variables kind of mix to help you plan out what trajectory, what path options you have to get back and forth between the planets. So options, include, well, we could have a really long stay at Mars, close to a year at Mars, an Earth year, I should say, at Mars, where you wait until the planets get aligned again to do a short trip home. Or in this current option, what we're doing is having a very short stay at Mars, about 30 sols on the surface, about 50 sols total in orbit, and then using that combination of propulsion systems in order to chase Earth on the way back home. And so you can see that that means like maybe the overall mission will still be pretty long, but it won't be as long as if you waited the whole time for the planets to come back in alignment. So you can see for this example, the crew actually go out past Mars orbit on the way back in, which is kind of a really unique trajectory option that isn't usually thought of, but was kind of a unique one that came out of this piece of analysis. So you can see here, these have the dates, or I guess the time durations. So for this specific example, this is just one example of a possible mission. The outbound transit takes about 300 days. Then you have your stay at Mars for about 50 days. And then your inbound transit is actually right around 500 days. So pretty long trip, lots of days in deep space. So you can see here on the table, again, we have that total distance traveled, about 1.8 billion kilometers, which is just mind-boggling. Our closest distance to the sun, again, is right about Earth distance. And then the farthest distance to the sun is 1.75 astronomical units. So that creates some additional challenges because, the farther out from the sun you get, the colder it's going to get. So the more thermal protection you're going to need on your spacecraft. Okay, so I think we should just be able to skip. There we go. Okay, so we talked about the propulsive system that's needed to get you out there. Where are the astronauts going to be living during these 300 days on the way out, 500 days on the way back? So the current concept is this Mars transit habitat. And so one really exciting thing is the new development of the inflatable technology. So you can see this kind of what looks like quilted material here, is condensed when it's going up in the rocket, so it can be folded down to a smaller size, which actually then when you get out into space and you reinflate it, allows you to have a much larger living space than the equivalent mass for a solid habitat. So that's making use of new materials development. They have a test inflatable module that's up on the International Space Station. So all of those different things are really exciting. Things that need to be included in this habitat. You need to consider what are your medical capabilities. Generally people like to go to the dentist every once in a while just to make sure their teeth are okay. Are you going to have a crew member who's trained in dentistry? What happens if someone gets sick? Can you take care of them? Can you do surgery in microgravity? You want to have good food. I don't know about you, but eating canned food for 2 years doesn't sound particularly appealing. So, you want to have a good mixture of food that the astronauts will be happy eating for this time. And they will also, it'll be still nutritious, things like that. They'll need exercise equipment so that, as their bodies adapt to microgravity, you're not causing harm. And, you're still preparing the astronauts for when they get to Mars and they have to then operate in Mars gravity environment and adapt to that relatively quickly. Let's see, what else do we have on here? Life support. So, what happens if something breaks, like, your oxygen system or your water system? Again, those pesky humans have to be kept alive somehow. So how do you know how many spare systems, how many spare parts do you need to take along with you? Doing that type of analysis from a risk perspective of, how much is enough and, how much is too much, where we're just wasting money, we're wasting space, we're wasting mass, sending all these extra pieces that we're not going to ever use. So back to those human issues. There are some pretty big issues with sending humans to space. Space radiation. Here on the surface of Earth, we have the nice big thick atmosphere that's helping keep us safe from the radiation coming from both the sun and from beyond the sun, the galactic cosmic rays, things like that. That radiation can cause increased cancer risk. It can make you very, very sick. And you don't want your astronauts getting sick during their mission or increasing their risk of getting sick after they complete their mission. One thing that, maybe we are understanding a little bit more after this past year of lockdowns, how does isolation affect how you operate as a human being? We want to keep the astronauts healthy. We want to keep them happy. We want to keep them able to work together. Not being able to see the sun or having the sun rise and set to have your normal circadian rhythm. Are the astronauts going to have experiments to do all those days on their way to and from Mars? Or are they going to get bored? Astronauts are usually very gung-ho people of like, let's do stuff. Are you going to be able to have enough stuff for them to do? Let's see, distance from Earth. Yeah, so the farther out you get, the more you have a communications delay, and you're not going to be able to rely on mission control or ground control to answer your every question right away. So the astronauts are going to have to be much more self-sufficient, able to solve problems on their own. Now, gravity. So we already talked about this a little bit, adapting to both the microgravity environment and then also readjusting to gravity, but a different gravity for the surface of Mars, and then back to microgravity again on your trip back. Then we also have what's called these hostile closed environments. You can't just step outside your habitat whenever you want. You have to plan with your spacesuit. You have to make sure you have everything that you need. So that means you need to keep your environment working well. A lot of times astronauts will say that the International Space Station smells a little funky and it's very loud. So, are you going to be able to stand that for 2 years? Or is that going to get really, really annoying? So once we get to Mars, what happens with stuff there? So things that we need to think about, Mars has dust storms that pop up frequently enough. And sometimes those can even grow to be global dust storms. And that's what actually took out the Opportunity rover, is that there was a global dust storm that covered the entire planet and it could not get enough solar power to stay alive. So, if there's a dust storm when we get to Mars, how long can you wait before you have to give up and go home? Or if you're already down on the surface, how fast can you get back to your ascent vehicle to get back up to orbit and return home? There's also the just navigating around Mars, with the sand, different hills, things like that. One of the big things for exploration is, we want to go look at these rocks that, the rovers have been investigating. We want to see if there's the potential for life there or if we can find life there. So we want to do that in a way that protects both the Mars environment, protects those samples, but also protects us, the humans, and Earth from bringing anything back with us too. Let's see. Yes, so we already talked about the round trips. So again, you're not going to really be able to just send supplies if you run out of something. So you want to make sure that you have everything that you need either sent ahead of time or sent with you. And yeah, the communications delay can get pretty bad. About 44 minutes round trip. Sometimes, depending on how the planets are aligned, you can actually get to the point where there's where the sun is in between Mars and Earth. So you get those blackout periods where you're just kind of on your own. And yeah, so there are some pretty big challenges to work around there. But while we're on the surface, the plan is that the astronauts will kind of go around in what we call this pressurized rover. So there are, a couple different concepts. And the idea is that we would do a test one on the moon as kind of practice. And so you can see kind of, here's one kind of that was, I think, tested out in the desert in Arizona in the southwestern United States. Here's a concept that the Japanese Space Agency has proposed. And then here's another concept of, that same rover-ish design on Mars. And so that would be where the astronauts would spend those 30 sols on the surface of Mars, roving around and exploring. So after we're done with all of our exploration, we have to get back somehow. And this is where it gets a little bit tricky because Mars has an atmosphere, but it's very, very thin compared to the atmosphere on Earth. So it's just enough that it makes things tricky. Now, kind of the big things to consider, over 20 tons of propellant are needed to get your ascent vehicle back up to orbit. That's just a ton of, 20 tons. But so there's a lot that's needed to make this work to get you back up to space. So we're actually going to go through a little bit of an example here, since I heard that you guys were maybe a little bit interested in, what actually do I do all day here at NASA? So some of the things that we do are kind of these initial vehicle design sizings, and figuring out what are the important factors for these designs. So kind of, looking at this Mars ascent vehicle problem, this is kind of like what drives the entirety of the rest of the architecture is what do we need to bring back from the surface? So that includes your Mars samples. So what rocks do you need? What are you going to take some Mars regolith, the soil samples? Are you going to try to take any frozen ice cores? And then, how many astronauts are you sending? How many supplies do they need for that trip back up to their transit vehicle? So then you say, okay, based on how many samples we want to take and how much space, how much packing volume those are going to need, how many astronauts we need, their supplies, and the life support systems, then we can kind of build a general size for this ascent vehicle, figure out how big it needs to be. And then we can take a pick of what engines do we want to use? What propellant types do we want to use? How many stages do we want these vehicles to be? Currently, the general concept for the Mars ascent vehicles, that it would be 2 stages to get you back up to orbit. But definitely a really cool area for exploration. And so then kind of once we have the general sizing figured out, then we can take a look at where does this ascent vehicle have to get you to? What orbit is this transit hab going to be in? How long is it going to take you from launch to meeting up with the transit vehicle? And from there, we can use this fun equation, the rocket equation. It just sounds really cool. So let's see here. Here's your what we call the delta V, which is your change in velocity. And so you can figure that out based on knowing what orbit you have to get to. So that's how you get that variable. And then your ISP is your specific impulse, and that is a characteristic of what engine you choose. So based on what engine you choose, you then know that variable. Your G naught is standard gravity, so that's Earth at sea level. So that's your gravity factor there. And then you have your natural log of this fraction from your mass initial to your mass final over the time it takes between those 2 points. So you can say, okay, if I know my change in velocity based on what orbit I need to get to, I know my engine, so I know my specific impulse. Earth gravity is constant. And I know my final mass, which we're going to say is approximately the Mars ascent vehicle with the gas tanks empty once we meet up with the transit hab. Then we can rearrange the equation and find your initial mass to figure out how much propellant you actually need. So that is kind of the process that we go through for some of these initial vehicle sizing and architecture analysis problems. So as I said before, we're going to be practicing for Mars at the moon. So that includes, practicing how do we get all these vehicle pieces going together. We're going to test out the Mars Transit Hab at the moon. We're going to see for the crew health how the astronauts adapt to space for longer duration missions. We're going to have pretty much the same design of the rover that they'll be able to use, testing out new spacesuits, figuring out our planetary protection procedures. So basically the whole idea is we're doing moon to Mars. We're going back to the moon in order to prep for Mars. And so here we can just see some of the comparisons, talking about those 5 hazards of human spaceflight and how we're going to use the moon to practice. So you can tell, yeah, of course, there are some differences at the moon, but still practicing at the moon is going to be a lot closer than practicing anywhere on Earth. And again, this is just another comparison slide of, kind of the differences in the architectures and how we're going to be doing those different things. So a little bit of the Australia connection, the Australian Space Agency is kind of more of a working to enable the industry factors. So it's different than NASA, whereas like NASA is kind of building our own missions and doing things. The Australian Space Agency is much more involved in getting private companies to do space exploration and things like that. But NASA is involved with Australia as part of the Deep Space Network. So the Deep Space Station number 43 in Canberra is actually, this is a 70-meter diameter parabolic antenna. And that's part of 3 major Deep Space Network locations across the world, so that, missions that are really far out, the Mars missions, some of the Voyager missions going out past the solar system, those can still communicate back with Earth and still send their data back to Earth so we can figure out what they're doing. And with that, I think we'll open it up for questions.
Fantastic. Thank you very much, Emily. If you're asking whether or not there are questions, I've just been gathering them as we're going along because the students have been putting them in the chat, and we've got dozens and dozens of questions to choose from. So first of all, thank you so much for the talk. It's absolutely mind-blowing that this is actually something that we're actually planning on doing. It's not sort of thinking about maybe one day we could. No, this is plans in motion. So could we maybe start there? A number of the questions have been around the notion of like, how much lead time do you need to have from maybe we should send people to Mars to, hey, we've just landed people on Mars. Like what's the full time scale of a mission like that from conception to success, let's say, rather than the alternative?
Yeah, so I think a lot of that is figuring out exactly what vehicles we are wanting to use as part of these mission architectures, and then kind of backing out the time it's going to take to develop those vehicles and develop the technologies that are needed. So basically, if we can kind of start with well, let's say we're going to Mars in such and such year. We're going to need to have the, landers developed at this time, and we're going to need to have the rockets developed at such and such time. So kind of, I have teammates that are working on both identifying the gaps in current knowledge and the gaps in current technology, and then working to figure out a timeline for how quickly do we think that technology can be developed. And do we have the funding resources in order to get those developments going on time and things like that. So for a mission of this scale, we're looking at, especially for some of the lunar missions that we're hoping to use as practice, the plan for the lunar missions is starting in the 2020s. So, we're hoping to have those architecture vehicles up and running by the end of the decade in order to use as practice. And the idea is, we don't want to build a lunar version, test it out, realize like, oh, that was a horrible design and it didn't work at all, or, just redo things entirely for Mars. We want to be able to use approximately the same systems so that we can take what we learned on the moon and, use those experiences to make things as similar as possible. That implies that, the astronauts will have less training between, the differences in the systems. It'll hopefully be saving cost by not having to redo developments. And hopefully, be saving time too by not having to redo those developments and redo all the testing. So, I would say for our current architecture plans, we're hoping to have some of these systems up and running on the moon by the end of the decade. So,
Wow.
if we're hoping to try and get to Mars as early as the 2030s.
That's pretty ambitious. And I mean, I like the notion of, like, from an engineering point of view, we're going to go to the moon and we'll use that as a bit of a testing ground. But by the same token, we don't want to have to do that too many times. We don't want to get things wrong and have to start again. So let's go to the moon and then assume we can actually take stuff to Mars. I think that's an interesting point of view. The question has literally just come through, which was also on my mind as well. How many people would you estimate it takes to get to Mars? And what I mean by that is, like, how many people are working on this at the moment? What's the size of this project in terms of people?
Yeah, so I would say, currently Mars is not an official program at NASA. So our Mars architecture team is fairly small within the overall, breadth of human exploration at NASA. But if you take into account the whole Moon to Mars idea, right now with the Artemis program ramping up to send astronauts back to the moon, there are hundreds, if not thousands of people working on that. So, the idea would be then, a lot of those people would then transfer over to Mars, or, there would be a blending of the people and the knowledge between those two programs. So right now, our Mars architecture team is, working closely with a lot of the Artemis teams to kind of make sure that what we're planning and actually fits with what they're planning to do on the moon, and making sure that they understand, hey, if we are trying to use the moon as practice for Mars, the systems that they're designing for the moon have to actually work on Mars. So it's been a lot of collaboration between the different groups and making sure that everyone is on the same page.
So how big are these groups? I mean, how big is the team that you're working with? When you say it's not a very big team, is it like 2 people? Is it 200 people? How big is the group?
Yeah, so our local Mars architecture team here at Langley, I would say we probably have about 12 people, but I think there's only 2 of us that are working full time on the team. Others are split. A lot of them are split working on the moon stuff too, or on other science projects, other space technology projects. So yeah, our team locally is pretty small. I would say across the agency, the Mars architecture team has, again, probably under 100 people at various levels of involvement. whereas some of the Artemis teams can have several hundred people working on just one vehicle because they're much closer to actually launching.
So if you're okay, I've taken notes for all.
Someone has their microphone on. There's some audio coming through, so whoever that is, if they could turn their microphone off. Thank you. Let's get into a little bit of the nitty-gritty, because there's a bunch of questions that have come through which are about the technical side of stuff. And so, as we said in our discussion in the lead up to this talk, Emily, there's a bunch of students who are just championing the bit to, yeah, but I want to use that equation. I want to do some stuff. You put up some trajectories of showing how we get from Earth to Mars. And one of the questions which came up was, why are we chasing Mars? Like, you sort of go from Earth and you follow it around this and you sort of chase it to catch up. Wouldn't it be easier to just go the other way and sort of meet it halfway around? So what's the problem with that? I have a feeling I know, but I'm curious to know whether I'm right. What's the problem with going the other way?
Yeah, so there are a couple issues with trying to go backwards around the solar system. But the main one it comes down to is the amount of propellant that's going to be required. So when we launch, as NASA, we're launching east over the Atlantic Ocean. And in general, launches like to go east because you get that added bonus of factoring in the spin from the Earth to help give you a little extra boost in your velocity. So, then if you're trying to take off going opposite planetary motion, you have to effectively cancel that velocity out and then also get your velocity to travel across the solar system. So, the propellant needed to do that, it would just be so much more than what it would be to chase Mars in the direction of planetary motion.
Right. So even though just drawing it on the simple plan of the solar system, it looks like it's a shorter distance or might be an easier trip in some ways, you've actually got to cancel out the fact that we're going really fast now, and that actually takes a lot of propellant. So am I right in summing up what you're saying, that if you use the fact that we're already moving, that actually makes it easier?
Yeah, so if you go back to that rocket equation, that's going to say, well, your delta V, your change in velocity is just going to be so large. The difference between your mass initial and your mass final, that propellant that you're going to need is just going to be too big to be realistic.
Gotcha. Some of the detailed questions that are coming through about the equipment that you're taking with you and the spacecraft that you'll be in for that period of time. How is it powered? Like, what's the plan for actually keeping the lights on in this thing for such a long period of time there and back?
Yeah, so solar panels are going to be part of the let's see, the transit hab will have solar powers, but since the transit hab is going to be a pretty big vehicle, there will also be some opportunities to use some alternate power sources, and that could be pulling from you could use some nuclear. That gets a little tricky with how do you protect the astronauts from that radiation. When you get down to the surface of Mars, currently we are looking at nuclear power just because of that issue with the dust storms. You don't want to be solely relying on solar power and then have the solar panels get covered with dust and you lose all your power. So, nuclear is a fairly reliable system that, you won't have to worry about whether or not you can see the sun in order to get that power on the surface.
Right. That kind of, it leads me to, like, when you're down on the surface, it leads me to another whole series of questions that have come through, which is, you talked about having to get an enormous amount of stuff to Mars in order to just sustain the mission and have stuff there for people to live in and work with. I'm guessing that it's a little bit further down the track, but are there considerations about using resources that are already at Mars? In other words, getting to Mars and going, let's dig stuff out of the ground and use that. what, you know,
Yeah,
is
so
that even a consideration?
Yeah, so one of the experiments that is currently on the Perseverance rover is called MOXIE, and it's basically a proof of concept to see about, you know, we said the atmosphere on Mars is primarily carbon dioxide. Well, one of the components for rocket fuel, you know, in order to have stuff burn, you need oxygen. So can we split the carbon dioxide and pull the oxygen out in order to use that oxygen as propellant? Or, you know, for the astronauts on the surface, can we use that for as part of their life support systems? So this MOXIE experiment was looking at, can we pull that oxygen out of the atmosphere? And it has been successful so far at a very, very little scale. So, you know, in order to use that for the humans, you'd need to scale up that system quite a bit. So that
that's
is
at
one of the
least,
options.
it's possible in principle. Yeah.
Yeah.
So I think we've got time for maybe a couple more questions. So I'm going to throw this one to you now, and then we'll see how this one goes. And I hope you don't mind. I'm going to ask you, I guess a little bit of a cheeky or a tricky question, but I'm also guessing that as someone who works on the project that you work on, it's probably not the first time this one's come up. So I'm going to give it a go anyway, and then you can totally dodge it if you want to, or address it face on. It's totally up to you. But there's a series of questions coming from the students who are looking at this from the point of view of, I guess you'd lump it into ethics, really, saying, we have so many things that we need to pay attention to here on this planet. How do you justify the amount of effort, resources, funding to send people to another planet, let alone the moon? And so I'm really interested as someone who, like, you're obviously pretty early in your career, and you're working in got to be one of the most exciting places to be an engineer. How do you think about that issue around the ethics of spending money and time and effort getting to another planet when there's lots of problems here that we can be solving?
Yeah, so for one point is, you know, oh, well, if we just had all the people that are working on these types of projects turn around and focus their attention on, you know, finding a vaccine for COVID, curing cancer, you know, solving climate change, things like that, you know, oh, could we solve all of Earth's problems? Well, you know, I'm not trained in immunology. You know, that's medical stuff is not a big interest of mine. So, you know, that's kind of one of those areas of, sure, we could probably figure it out, but we would not be the most efficient people to solve some of those problems. On the other end, you know, NASA does a lot of fundamental research for climate science, earth science. We're using some of the NASA Earth observation satellites to actually look down at the Earth. One of my favorite examples is, you know, we're helping farmers figure out when is the best time to plant. We're looking at soil conditions, how much water is in the soil, is there currently a drought going on, do we have wildfires popping up? And so kind of all of that data can be used to help the farmers grow their crops most efficiently and at the right times to avoid some of those agricultural disasters. We, you know, are also doing, you know, there is medical research with figuring out stuff with the astronauts, how their bodies change in space. Some of those, you know, medical advances are coming from that type of research. We have a large contingency of flight surgeons, aerospace doctors that are doing a lot of that research on the human body. And kind of overall in general, you know, the way I see it is NASA is pushing the boundaries of the technology development for, you know, the US and the world in general. And a lot of the technology that is developed as part of, you know, solving these challenging problems for space exploration actually does filter down into common practice. So one of the really cool examples is by trying to reduce mass and make better optics for cameras. That technology is actually used in pretty much every cell phone camera now in the world. And that was developed for a space mission by one of the engineers at the Jet Propulsion Laboratory in California. Another example, by trying to keep the astronauts safe as part of, launch and landing conditions when it's really rough on their bodies, memory foam. That was one of the developments by NASA. So, there's all these developments that, we come up with these ideas to solve very specific problems for space exploration that then can be applied to solving real problems here on Earth in everyday life. So the way I see it is, by pushing these boundaries of technology development, we are influencing the technology and how people live here on the planet Earth. And we're also providing inspiration for people. There's more to life than just surviving. If you're not enjoying life or learning from life, that's not too great. So by providing these really cool out of the world missions, we're helping provide that curiosity, that area for exploration to inspire people around the world.
I think you've hit on a couple of really nice things there. I like the notion. First of all, I mean, if you look at things like, return on investment from something like the Apollo mission, where we went to the moon the first time, it cost a load of money to do that, but the amount that NASA, the US, the world got back from that, from a technology point of view, far outweighed the amount of money that went into it in the first place. So there's probably a reason to believe that you'd get the same kind of return on investment here. We seem to be strangely wired as a species to need these big, strange, exciting exploration goals rather than focusing on what seems like a scary, dangerous thing like climate change. We need to do both, obviously, but it's not necessarily a one or the other. Is what I'm taking out of your answer there. Listen, I think we are going to have to finish that one up there because we've come to the end of our allotted time. There are plenty of other questions that I could have thrown at you, Emily. And so maybe if you would be prepared for this, maybe I could gather those up and send them your way. And I'm not expecting necessarily an answer to every single question, but would you be prepared to at least get down a few thoughts on some of the questions that stand out to you from the ones that have been thrown into the chat for the students today? That'd be great. Yeah. Okay. Well, then could I get everyone to, in the time-honored tradition, give a huge round of applause wherever you are to Emily Judd from NASA for the fabulous talk today. And I would like to hand over to one of our fabulous ISS scholars. I'm going to hand over to Ankita from the Green Group. Ankita's there, ready to go, to give the formal thank you on behalf of us all. Ankita, take it away.
Hi, Emily Judd. I'd like to extend a huge thank you on behalf of all of us here at ISS. We would like to express our gratitude for your time and effort to provide us with an insight into your amazing and truly fascinating work. I think I stand with everyone when I say we thoroughly enjoyed this presentation very, very much. So thank you for taking time out of your busy schedule to give us this engaging and thought-provoking lecture about the NASA Mars mission. Once again, thank you very, very much, Emily.
Thank you, Ankita.
Thank you.
And can we have one more final huge round of applause? We can hear it virtually through the airwaves for Emily Judd from NASA. Thank you so much, Emily. And if you'd like to stick around for just a